So in Chapter 3 we learned about vectors, and one of the reasons we learn about new mathematical techniques like that is so that we can actually do more physics. So the reason to learn math is to do more physics. Tell your math instructor that. And so that's what we wish to do. We actually have learned about kinematics in one dimension, but we wish to expand kinematics to more than one dimension, 2 dimensions, possibly 3. So take a look at this. We have an x and y coordinate system, and we have a path, and a particle is going to move along this path. So it's moving in a 2-dimensional coordinate system. We can define its positions in terms of vectors from an origin. So I could say it has an initial position defined from an origin, r sub I, and that's a vector of magnitude and direction that defines that point. And I can think of a final position, r sub f, as a vector extending from the origin to that point, so that my displacement is my change in position, my final position minus my initial position in a vector sense. And my displacement in this case is a vector that connects these 2 points. In a sense, I could say that my initial position, r sub I, plus my change in position, delta r, is equal to my final position, r sub f. So we're looking at this graph, and we've defined simply a new displacement in terms of vectors. It is my final position minus my initial position, but it's a vector that defines that displacement, direction, and magnitude. Okay, so that's all that's really important to get going on kinematics in more than one dimension, is to realize this displacement vector. Now we had to define this in terms of an origin. We had an initial position and a final position, but you may notice that we actually could have chosen any origin we wish, because if I were to move this origin, say, over to the left here, my initial position would still go to the same point. My final vector position would go to the same final point, and my delta r would still be the same, even if those vectors were, those initial and final position vectors were longer vectors. Wherever I define my origin, the delta r is still going to be the same no matter what. So this displacement vector is a good place to start. Once I define my displacement vector between 2 points, my final and initial position in terms of direction and magnitude, all my other variables in vector form follow. I have my average velocity, which is my change in my position over time, or my displacement over time. I can have my instantaneous velocity, which is my infinitesimal change in position in an infinitesimal amount of time, like before. In this case, they're vectors still. The velocity and my position is a vector. I can have average acceleration, which is my change in velocity per time, still a vector, because I'm just taking a vector, dividing it by a scalar, change in time. And my instantaneous acceleration is my infinitesimal change in velocity in an infinitesimal amount of time, my dB dt. All these stem from the fact that I've defined a displacement vector. Let's take a look at these types of expressions. Here's a problem. The vector position of a particle varies in time according to position r is equal to 3I plus a negative 6t squared j in meters. Find expressions for the velocity and the acceleration as functions of time. Well, this is my position for all time. My velocity is the derivative of the position as a function of time. So if I were to take the derivative of this vector, it's a derivative of what's in front of the i's and j's and k's. And the derivative of 3 is 0. The derivative of negative 6t squared, decrement the t squared, gives me a negative 12t j. So my velocity for all times is a negative 12t in the j direction. My acceleration is the derivative of the velocity with respect to time, if I took the derivative of this velocity for all time, negative 12t, the derivative of that is just a negative 12, and hence my acceleration is just a negative 12j. So in this case, it's constant in the j direction. Determine the particle's position, velocity, and acceleration at t equal 1 second. Or we're just going to plug in t equal 1 second into these expressions. For my position, that's going to be 3I plus a negative 6 1 second squared, which is just 3I minus 6j meters. That'll be my position. My velocity for all time is a negative 12t, but at 1 second, it's going to be a negative 12 times 1 second, or just a negative 12j meters per second. And my acceleration is just a negative 12j for all time and all position. T doesn't come into it, it's just constant. So it's just a negative 12j meters per second squared. Alright, so we define these kinematic equations in vector form. These kinematic variables in vector form. Here's our first kinematic equation, number 1, in vector form. Final velocity equals initial velocity plus acceleration times time. If I were to write this like vectors with magnitude and direction, I might have something like an initial velocity like this, v naught, going some direction, and then another vector, acceleration times time, going, say, in a different direction. And the sum of these, at tip to tail, comprises my resultant vector, in this case, the final velocity. So my final velocity is equal to v naught plus at. This could be something like, say you were flying an airplane with some specific heading with an initial velocity v naught, and you're moving in one direction, and there's a crosswind that hits you and forces you into another direction, and acceleration times time over a certain time, and hence you actually end up going in a different direction with a different speed. But it's the addition of your initial velocity plus that acceleration times time gives you your final velocity. We can also try this with our displacement. If we choose our initial position as 0, then our position becomes the same as where our displacement was. And our position as a function of time will be our initial velocity times time plus 1/2 acceleration times time squared. I can view this as vectors with a v naught t giving me a definite displacement in some direction, and there might be another displacement due to acceleration of 1/2 at squared. Both of these have units of meters and they have definite individual directions. A sum of these two gives me my final position. So my final position is v naught t plus 1/2 at squared. Kinematic equation number 4. But we can see that strictly in terms of magnitude and direction, the sum of vectors. We're going to look at projectile motion, and we're going to think of projectile motion in particular as two-dimensional motion and the simultaneous superposition of two individual motions, motion in the x direction plus motion in the y direction. Simultaneous means that these motions are taking place at the same time, and superposition, which is a basic principle of physics, means that the resultant effect is the combination of the individual effects, individual motions in these cases. This comes up again and again in physics, where you look at the individual contributions and then the combined contribution gives you your net effect. Here's an example of simultaneous superposition of motions. Imagine a target. SpongeBob is a good volunteer for this since he's kind of spongy, so if something hits him, it's not going to hurt him. And we're going to aim a projectile at this target with some initial velocity, and it will travel with some time t. So given that this were done in non-accelerated space, if we were to shoot this projectile at that target, it will hit the target after a time t. Let's say, though, that we actually do this near the Earth, under the acceleration of gravity, and SpongeBob is hanging on to some kind of tree, and he decides, as soon as you shoot this projectile, that he's going to let go of the tree and fall, and hopefully he's thinking that if you aimed above him where he was, that the projectile will go above him and miss him as he's falling. So he's going to decide simultaneously that he's going to let go and fall as soon as you shoot this projectile. And he's going to laugh, that irritating laugh, as he's falling, because he's thinking he's going to get missed. So he's going to fall, and he'll go through some displacement in his fall of 1/2 at squared. However, your projectile has two displacements going on simultaneously. It's doing the v0 t plus the 1/2 at squared. So your projectile actually follows a parabola, and it's going to go through parabolic motion. So all the while, it's going v0 t and falling 1/2 at squared combined, and hence it's going through this curve. So after a time t, it's going to find itself at the same position where SpongeBob is. All he's doing is 1/2 at squared. The projectile's doing v0 t plus 1/2 at squared. They hit at the same spot. Projectile motion can be thought of as the simultaneous superposition of two motions, constant velocity in the x direction horizontally, and constant accelerated motion vertically with the acceleration of gravity, which is 9.80 meters per second squared, down towards the center of the Earth. So the constant velocity motion will have no acceleration, and the constant accelerated motion will have a constant acceleration down. So we'll think of this projectile motion with initial velocity and a launch angle theta naught as horizontal motion at constant velocity. So whatever velocity we have horizontally will continue forever and ever and ever until we hit something. And then in the vertical motion, we're going to start with initial velocity, and we'll have the acceleration of gravity in the opposite direction, 9.80 meters per second squared, down the whole time. What we wish to do is superimpose these two, and the thing that brings them together, the thing that allows us to see what the superposition will be, is time, because they're both going to happen at the same time. So we can deal with one motion in a straightforward kinematic sense, deal with the other motion in a straightforward kinematic sense, combine the two motions by the fact that they both are happening with the same t. This parabolic motion happens a lot, especially in sports. Imagine this forward pass, and we're showing the football at different time intervals in this forward pass. And even though you know of some quarterbacks like Peyton Manning or Tom Brady or some future quarterback who can throw this football on the line, what it actually is doing all the time is going through some kind of parabolic motion. But as we look at a snapshot of this football in the air, we see that it's actually spending more of its time in the upper end of its parabolic motion than it is in the lower end. This is because as an object is going up, it spends when you first throw it, it's got a very large velocity, and then acceleration slows it down, so it starts slowing down, slows down. Actually, momentarily is at zero at the apex of the parabolic motion, then starts picking up speed slowly, and picks up speed, and then hits with the same speed you first threw it at least vertically. So it's fast, slow, zero, slow, fast. It's spending more of its time in the upper half of its parabolic motion. This happens in sports. Anytime you jump, you're spending more of your time towards the top of your jump than you are at the bottom of your jump. A basketball player attempting to score seems to look like he or she hangs in midair because they're spending a lot of time near the top of their jump when they're making the shot. 2/3 of the time in the air is spent in the upper 1/2 of the height where the vertical velocity is smallest. Same thing happens for a volleyball player. A volleyball player goes up, it's ready to spike. Maybe the set isn't quite what they expected, and they can adjust to a bad set and hit the ball after that. If we launch a projectile with some initial velocity v naught at some angle theta, we can extract just the x motion and look at the x motion first. And that's what we're going to do. So we're going to say that in the x direction at least, there's no acceleration. We'll look at our initial velocity as the x component of this velocity, which is going to be v naught cosine theta. Our final velocity will be v naught cosine theta as well. We're going to have no acceleration, so whatever velocity we have will be our velocity for all time, initial and final, and also average for that matter. So our displacement is going to equal our average velocity times time, which is our velocity times time. No acceleration, so there's no 1/2 at squared because a is 0. And we're going to define it by some time t. So these are the equations that describe our kinematic variables. What about the y motion? Looking at the same projectile shot with the same v naught at the same angle, we have an acceleration of negative 9.8 meters per second squared, because we're defining our positive y, initial y velocity up as being our positive direction. So acceleration is going to be negative 9.8. Our initial velocity would be v naught sine theta. Our final velocity will be v naught plus acceleration times time. So we'll be governed by the kinematic equation for the vertical motion strictly by our initial velocity plus acceleration times time. And our displacement will be kinematic equation number 4. Displacement is equal to initial velocity times time plus 1/2 acceleration times time squared. In this case, the acceleration is a negative 9.8. And we have time. So these are our kinematic variables in the y direction, and we'll just look at that motion as well. And we'll combine everything by our time. Kind of a sidelight to this is some implication as to what our maximum height, our time maximum height, and our range will be. So let's just take a look at that. Our maximum height for projectile, which we define as h, is dependent on our vertical motion. And we'll say that our final velocity squared equals our initial velocity squared plus 2 times acceleration delta y. But if we're talking about the vertical motion and we're going to maximum height, we will reach maximum height when our vertical velocity becomes 0. So our final velocity vy will be 0 at maximum height. Also, our acceleration is a negative 9.8, so that's going to be a negative g. Delta y is going to be equal to h, our height, and our initial velocity in the y direction is going to be v naught sine theta naught, or sine theta, if you will. So we can substitute all those in. We have 0 is equal to v naught squared sine squared theta minus 2gh, because our acceleration was a negative g. Solving for h, we have that our maximum height is our initial speed, v naught squared, times sine squared of our initial launch angle, theta, over 2 times 9.8. That's how high we'll go. Neglecting air friction, that's how high this projectile will go. Time to the maximum height, again, we'll realize that our final y velocity will be 0. We'll go as high as we can go and go no further. So at our final height, we'll have a 0 velocity. Acceleration of a negative g. So we know our final velocity will equal our initial velocity plus acceleration times time. We can write that as v final, vy, is equal to our initial velocity, v naught sine theta, plus a negative g times time. Our final velocity is 0. Solve this for time, and time will equal our initial velocity sine theta divided by g. That's the time it takes to get to maximum height. The time it takes us to fall from maximum height back down to ground level will be exactly equal to that time, because that motion mirrors the motion going up to maximum height. So our time for the full range to go up and then back down to ground will be twice this time, 2v naught sine theta over g. Since that's our time in the air, that 2v naught sine theta over g, we can now calculate what our range is. Our range is going to be equal to our x velocity times the time that we're in the air. That's going to be v naught cosine theta times this 2v naught sine theta over g, which we could rearrange as v naught squared 2 sine theta cosine theta over g. But the identity 2 sine theta cosine theta, that is a trig identity, otherwise known as the sine of 2 theta. So we have that our range, how far we're going to go on a level plane, is going to be equal to v naught squared sine 2 theta over g. Let's take a look at this. This is our range, v naught squared sine 2 theta over g. Because of the form of this equation, complementary angles of the angle theta will result in the same range. So if I were to shoot at 30 degrees, that will have the same range, shooting with the same initial speed as a projectile with an angle of 60 degrees. Why? Because the sine of 2 times 30, which is the sine of 60, is the same as the sine of 2 times 60, which is the sine of 120. They both are going up like this. They both have the same value in a positive direction. So sine of 2 theta is the same for complementary angles. Complementary angles are angles that add up to 90 degrees. So the range of a projectile shot at 20 degrees will be the same as a projectile shot at 70 degrees. Or a projectile shot at 10 degrees will have the same range as a projectile shot at 80 degrees. Or a projectile shot at 1 degree will have the same range as a projectile shot at 89 degrees, going straight up and coming straight down almost. Don't do this at home, but complementary angles will have the same range. Maximum range will occur when the sine of 2 theta is equal to 1, because in this equation, if the sine of 2 theta is equal to 1, then I'll get my maximum possible value. Sine can't be greater than 1. And that will occur when the total angle inside the sine function is 90 degrees, because the sine of 90 is 1. So that means that theta would have to be 45 degrees. So we'll get a maximum range at an angle of 45 degrees, assuming no air friction. And so our maximum range indeed will be v naught squared over g. If I shot this thing for maximum range at, say, 10 meters per second, maximum range will be 10 squared over 9.8, which is approximately 10. So it will go a little bit more than 10 meters. 10 squared divided by 10. Let's try an example of a two-dimensional problem. Most of our problems we're going to break up into x and y, and this will be an example of that. In a local bar, a customer slides an empty beer mug down the counter for a refill. The bartender momentarily is distracted and does not see the mug, which slides off the counter and strikes the floor 1.4 meters from the base of the counter. If the height of the counter is 0.86 meters, what is the time it takes for the mug to fall to the floor? So we're throwing a mug across a counter. It could be a beer mug, could be milk or something, doesn't matter. We have a mug going off the counter and sliding off with some initial velocity. Vertically, it's just going to start, once it leaves the counter, from a velocity of 0 and fall down to the floor. So that's what's going to determine how much time it's going to be in the air. So if we want to find the time it takes to get to the floor, we need to look at our vertical motion. 0.86 meters and do our kinematics based on that. Our x motion will be 1.4 meters, but we're going to work with our displacement will equal our initial velocity times time plus 1/2 acceleration times time squared, only in the vertical direction. Now we're going to start with initial velocity of 0. We're going to go displacement down to the floor. We're going to think of that as a positive displacement from where we are down to the floor. So we're thinking it as down direction as a positive direction. That makes our acceleration a positive 9.8 meters per second squared, and Vy naught will be 0. Solving for t then, multiplying both sides by 2, dividing by a, and taking the square root. My time in the air before I hit the ground will be 2 delta y over a square root. That's going to be 2 times 0.86 meters divided by 9.8 square root. It'll be in the air for 0.42 seconds before we hit the ground. Now that I have the time, I know that'll be the same time that's moving in the x direction. So I'm going to use that time to help me do the kinematics for the x direction. Let's find the initial velocity of the mug. We can use the x direction motion to do this. We know that our displacement will equal our x velocity times time. No acceleration to worry about because the acceleration in the x direction is 0. So our time will equal our displacement divided by time. 1.4, our velocity will equal our displacement divided by time in the x direction. 1.4 meters divided by 0.42 seconds. 3.34 meters per second. So for all that time, we were moving at constant velocity in the x direction, 3.34 meters per second, and that must have been our velocity when we left the counter, 3.34 meters per second. We had no velocity in the y direction. All our velocity was x direction, and it was 3.34 meters per second. What's the final velocity of the mug? Well, we left the counter, and we're going to hit with the same x velocity, but we're going to have a different y velocity. We're going to start from 0, and we're going to accelerate under gravity until we hit the ground. So our y velocity is going to be based on that. So we're going to have two components of velocity, x and y, and the vector sum of these two will be our final velocity. We'll define down as positive, so our final y velocity will equal our initial y velocity plus acceleration times time. In this case, acceleration is a positive g, 9.8. Our initial y velocity is 0, so we have 0 plus 9.8 times 0.42 seconds. We're going to hit the ground with a y velocity of 4.1 meters per second. Our x velocity is still the same, so the magnitude of our final velocity by the Pythagorean theorem will be these two components. Since they're perpendicular, it'll be our velocity x squared plus our velocity y squared, square root. That is going to be 3.34 squared plus 4.1 squared, square root. We're going to hit with a speed of 5.29 meters per second. Our angle will be the inverse tangent of our y over our x. 4.1 divided by 3.4 inverse tangent is 50.8 degrees, and that'll be this angle below the horizontal. So we're going to hit at an angle of 50.8 degrees below the horizontal when we hit the ground. Let's try one more example. A place kicker must kick a football from a point 36 meters from a goal, and the ball must clear the crossbar, which is 3.05 meters high. When kicked, the ball leaves the ground with a speed of 20 meters per second at an angle of 53 degrees to the horizontal. By how much does the ball clear or fall short of clearing the crossbar? Alright, so we have a crossbar that's 10 feet off the ground, 3.05 meters. To do this problem, we want to deal with it as individually in the x direction and then in the y direction, and the glue between these two directions is the time. So we want to use the x direction to find out how long it's going to take to get to the crossbar, and then use that time to find out how far we are above the ground when it gets there. So we'll see if we score the field goal. Our velocity in the x direction will be constant. It will be our initial velocity component in that direction. V naught is 20. But then our component in the x direction will be the cosine of 53 degrees. So 20 times cosine of 53 degrees is 20 times 0.6, or 12 meters per second. Basically 53 degrees is one of those internal angles of a 3, 4, 5 triangle. That's how I knew that the cosine of 53 degrees was 3/5. But if you do it on the calculator, you'll get that as well. The time for the ball to get to the goal, well, we know that our x velocity is constant, so our displacement will equal our x velocity times time, so the time will equal our displacement divided by our x velocity. 36 meters divided by 12 meters per second. It's going to take 3 seconds to get to the goal. So the coach has to make sure that there's no more than 3 seconds left on the clock, because if he leaves more than 3 seconds on the clock, even if you score and go ahead, you're still going to have to kick off again, and there's a possibility that the other team could return it for a touchdown. So this is one thing that the coach has to calculate in his head, how long it's going to take the field goal to get to the goal, so that he or she can let the clock run down so that there's no more time left after the field goal is kicked. So it gives you more respect for the things that a football coach has to do on the fly near the end of a game. They have to make these physics calculations in their head. So our initial velocity in the y direction is 20 sine 53 degrees. That's going to be 20 times 4/5, 16 meters per second. That'll be our initial velocity in the y direction. But we're going to have an acceleration there. Defining up as positive, our displacement, delta y, I should have a delta there, is equal to our initial velocity times time, plus 1/2 acceleration times time squared, but acceleration will be a negative g in this case. So we're going to have 16 times 3 seconds, minus 1/2, 9.8 times 3 seconds squared. After 3 seconds, we will be at a height of 3.94 meters. The goal is 3.05 meters high, so the ball should clear the goal by 0.89 meters. 3.94 minus 3.05 is 0.89 meters, which is a little bit less than a meter. It doesn't matter if it's good. Hopefully there's no crosswind, so it's wide right or wide left, and then, the other team wins. Roll Tide. So the y velocity at the time the ball reaches the crossbar is our initial velocity plus acceleration times time, but the acceleration is a negative g in this case, and our initial velocity is 16. So we're going to have 16 minus 9.8 times 3 seconds, and negative 13.4 meters per second is how fast the ball is coming down vertically when it reaches the crossbar. The negative means that the ball is on its way down, because we define up as positive and we end up with a final velocity that's negative. So it must have reached its apex already and must be on its way down. Alright, so that's an introduction to projectile motion, the equations and the technique that you need to approach these problems. Take a look at the problems in the problem set, look at those examples posted online, and practice as much as you can.